Okay, let's get started. Thank you guys for coming. Um, it's my great pleasure to introduce Dr. Chris Barty. Many of you guys know him very well, but if you're new to UCI, Dr. Barty is the distinguished professor in physics. He's also our BLI faculty, and he's famous in revolutionizing the radiation sources with new physics principles. For example, like laser Compton scattering X-rays. And he's not just a leading figure in academia, he's also a co-founder of New Neutron Technologies, and the company is focusing on commercialize his innovative technology, and they tried very hard to push it into clinic. And since he joined us in 2020, right?
2017.
Oh, 2017. Oh, okay. I joined in 2020. So everybody is really looking forward to use his groundbreaking X-ray source, including me. And I'm so excited to say what are the progress they have made in the past several years. Just really, it's our great pleasure to have him here today. Just please join me and welcome Dr. Barty.
Thank you, Sean. As Sean mentioned, I have one hat. I have another hat. Right. I am a co-founder of a company called Lumitron Technologies. The hardware for the machine that we're going to talk about exists in that building. It's at the corner of Bison and California, or Drake in California. Basically, it's across from the new Samueli Medical Building, diagonally across from that space in the UCI Research Park. My academic labs are also in the UCI Research Park in the Beal Applied Innovation Center, which is a couple of buildings over from that, as are several of the Convergence Optical Sciences Initiative faculty, of which Sean and Howard are both members of that faculty as well. I'm going to talk about distributed charge Compton sources today. Distributed charge Compton sources allow you to make precision X-rays and precision electron beam capabilities. And with that, you can detect disease more accurately, and you can treat disease, and in principle, do it without moving the patient. To remind you, there's some 2 million plus breast cancer patients a year, or breast cancer diagnoses a year, about 700,000 deaths from breast cancer each year. Prostate cancer, there's about half as many and about half as many deaths. If we do what we're trying to do correctly, the vision is that you would never remove a breast or a prostate again. You would find the disease early enough, and you would treat it before it ever became a problem, and you wouldn't have to be a barbarian and go hack people up, right? I'm going to talk about X-rays first. From the X-ray perspective, everything that's in the clinic is based on what this guy discovered in 1895. That's Wilhelm Röntgen. He was not trying to make X-rays. He was trying to take a picture of an electron beam. And he set up his camera in his lab to take the picture of the X-ray, of the electron beam. And he, went and developed the film and saw something on the film, and then went back and looked in the lab and found that he had actually blocked the camera from the experiment. And so something had gone through the thing that had blocked the camera, and that was X-rays. He won the first Nobel Prize in Physics in 1896. For you young people, Nobel Prize in Physics is not a Lifetime Achievement Award. It is an impact award. And of course, there's been tremendous impact from the Röntgen tube. Every X-ray tube in a hospital today is based on on the same process. That process is the stochastic stopping of electrons in a solid. That is, we make an electron beam of a certain energy, we throw them at the solid, and as the electrons go into the solid, they will eventually experience the nucleus of the atoms in the solid, and they will change their direction. A changing direction is an acceleration. An accelerating electron radiates, and if I go close to the nucleus, I will get a certain energy photon. If I go closer to the nucleus, I'll get a higher energy photon. If I hit the nucleus, I will get the highest energy photon. And occasionally I can knock out one of the electrons, and I'll get characteristic X-rays that have to do with the element. And so the spectrum that I get will look something like this, where the endpoint energy is the maximum energy of the electron that went in and hit the solid, and I go all the way down to zero, right? In this case, this is a 100 kilovolt X-ray tube. 100 kilovolt X-ray tube can be used for a number of things. Standard mammography operates at around 16 kilovolts. That is the place where the difference between fatty tissue and carcinoma is optimized. Lower, I get more contrast, but I get more dose. Higher, I get less contrast and I don't get to see the cancer. Angiography, where we look for blood vessel blockages in the blood vessels, that's done around 30 kilovolts. And whole body CTs are done around 70 kilovolts. If I'm doing angiography and I want to have 30 kilovolt X-rays and I use this tube, the photons that are below 30 kilovolts are not forming the image that I care about. They don't make it through the body. And the photons that are above don't have enough contrast to give me an image, and every one of those that's absorbed is just giving dose. So that portion of the spectrum is not doing any good, it's just doing harm to the patient. And so from an imaging perspective, you would like to have a monoenergetic source. We make X-rays a little bit differently. What we do is we take an electron beam, and instead of making it be 100,000 electron volts in energy, we make it be 100 million electron volts in energy. And then we collide that electron with a laser field. And what happens when we do that, so do this little animation, is that the electric field of the laser will cause a transverse motion in the electron. That transverse motion is an oscillating electron dipole. An oscillating electron dipole is just a radio antenna. But that radio antenna is moving at nearly the speed of light. So what you see coming at you is Doppler shifted into the X-ray regime. If I change the speed of the electron, I change the color of the X-ray that comes out of the system. So I can make a monoenergetic X-ray beam this way. The electron beam that I use, that 100 million electron volt electron beam, is sufficient energy that it could penetrate your entire body and be used to treat cancer anywhere in the body. We're going to come back to using the electron beam for treating cancer in a little bit. I can make one color. So if I want to do mammography, or if I want to do angiography, if I want to do whole body CT, I can reduce the dose to the patient tremendously because I can get rid of all that unwanted dose. There are many modalities where you can reduce the dose 100x over what's currently used. I'll show you a 50x version going forward. The brightness. Brightness is a characteristic of every light source. It is the number of photons that come out of a unit area and a unit time and a unit solid angle and a unit color. Right? The brightness is about 10 million times that of a regular Röntgen tube. If I'm doing imaging, and I'm doing shadowgraphy, which is what all medical imaging is, the size of the source determines the resolution of the image that I have. This little animation, I've got the skeleton, I've got a very big diffuse source, and if that source gets smaller, of course, I get much more crisp pictures of the skeleton as the source size gets smaller. If I take a normal Röntgen tube that's used in a hospital, the spot size is typically around 500 to 600 microns. This is the spot size of a Compton source relative to that spot size of a Röntgen tube. Right? So there is a tremendous potential for having higher spatial resolution imaging. I will show you some of that later on. There are devices that make X-rays in a similar fashion. They're called synchrotrons. Synchrotrons are billion-dollar scale investments, typically $500 million to $1 billion for the synchrotron. About 60 of these around the world. They're high science facilities where you plan your experiment a year in advance. You make a proposal for beam time. You find out 6 months before your proposal, and then you get 1 week to 24 hours a day to go collect your data. And you better hope you got it right because you'd have to wait a year to get back on the machine again. In a synchrotron, the electron goes around in a giant circle. That's the reason why they're big. The circle is, the diameter of that's about 1 kilometer. They go around at higher energy than we use, about a factor of 10 higher energy than we use. And periodically around that circle, they will have arrays of magnets. And those arrays of magnets will have north-south, south-north, north-south, south-north, alternating poles. As an electron goes through that magnetic field, that alternating magnetic field, it will see a J cross B force, a Lorentz force, that kicks it back and forth. And now I have an oscillating dipole again that is moving at nearly the speed of light, and what I get is an X-ray beam that comes out. The difference is that the spacing of the magnets in the synchrotron is 1 centimeter, and the spacing of the electric field variation in a laser Compton source is the wavelength of the light. It can be 0.5 micron or so. So there's about a factor of 10,000x difference in those scales. So there's a tremendous potential for having a compact source. You lose about a factor of 10 because they're going 10 times higher energy than we are, but you're still 1,000 times smaller. The synchrotron on the left is the largest in the world. It's in Japan. It can make X-rays up to 100 kilovolts. The Compton source on the right, that's, I don't know, 800 meters from here, is 1,000 kilovolt footprint, right? So it's a difference, tremendous difference in size. You look at synchrotrons, and synchrotrons will often describe their output in a brilliance curve, right? And if you look at this curve, this is the advanced photon source at Argonne National Lab. It's the second largest in the world. It's the largest in the US. Most of the photons are coming out at 10 kilovolts. Why 10 kilovolts? 10 kilovolts is an X-ray wavelength that's about the spacing of an atom in a molecule. So if you're going to do diffraction on a molecule, it's really useful to have the wavelength of the X-ray be the same spacing as the things that you're trying to diffract off of. So most of the experiments are done at 10 kilovolts. You notice that as it gets to 100 kilovolts and over 100 kilovolts, it dies faster than exponentially in its brilliance. A Compton source, excuse me, wrong click, Rankine tubes are way off scale, right? They're 10 orders of magnitude different. An optimized Compton source, however, gets better the higher the energy of the electron is. It gets better because I can focus the electron to a smaller spot, the higher the energy the electron beam I have. The electrons don't like each other. They want to get away, and the faster I make the electrons, the tighter I can focus that spot, right? And roughly you get a square smaller, you get a linear decrease in dimension of the electron beam spot size as a linear increase in electron energy. So you get square smaller spot as a cross-section thing, so you get square more photons out of a square smaller spot. The brightness is going as the number of photons and the spot area. So the brightness is going up something like the fourth power of the electron beam energy. Out there at 2 megavolts, you're 15 more orders of magnitude brighter than a synchrotron. There's a little joke that I like to tell that, when you go into a new field of science, you want to be 3 orders of magnitude beyond what the competition is. Because by the time you get where you're going, the competition will catch up an order of magnitude. You will have found out you were wrong by an order of magnitude, and you'll still be an order of magnitude ahead. You don't get 15 orders of magnitude very often in your life, right? And when I saw this in 2003, I basically pivoted my career. I was ultra high intensity laser guy up until that point. And I said, I'm going to go play in this field. And the question is, what do you do at a megavolt? Well, at 100 kilovolts, the X-ray, when it goes into the atom, interacts primarily with the electrons. At a megavolt, the X-ray, when it goes into the atom, interacts with the protons in the nucleus. The protons in the nucleus have a rich resonant structure, just like the electrons, the valence electrons of the atom. The reason why the shirt has all the colors in it is because those valence electrons have different resonant frequencies. The protons in the nucleus have the same thing, but the protons in the nucleus aren't governed in their motion by just the electromagnetic force. They're also governed by the strong force that's holding the nucleus together. So those signatures are not a signature of the element, they are a signature of the isotope. They depend on the number of protons and the number of neutrons that are in the system, right? So I wrote a little white paper back in 2004 that said, you're going to do nuclear physics with photons, right? And there are all sorts of nuclear physics things that you can do with photons. And it basically started a new field of study that's called nuclear photonics. We held our first International Nuclear Photonics meeting in 2016 in Monterey. The next one is happening in 2025. It's going to be in Darmstadt, Germany this fall. And there's a large number of people that are trying to do nuclear physics with photons. I pointed out at Livermore that you could find nuclear weapons material using resonant nuclear photons produced by laser Compton source. That was very important because that led to a lot of funding. Most of this work was developed at Livermore. I was the CTO for the National Ignition Facility and Photon Science Directorate. That's about a $500 million organization within the $2 billion laboratory. There's nominally 1,000 people in that directorate, and they've been working on lasers and optics with 1,000 people since the early 70s. So there's about 50,000 person years of experience in lasers and optics at Livermore. It is the home of the National Ignition Facility, which is the world's largest laser. The National Ignition Facility demonstrated fusion in December of 2022. That is, they got more energy out in laser fusion than laser light that went in. I'm one of 950 authors on the PRL for that paper. So But for this discussion, it's about the 3 generations of Compton sources we built at Livermore. So back in 2003, we'd finished our first Compton experiment that was to try and do time-resolved diffraction of shocked dense materials weapons physics, right? And in late 2003, I realized this 15 orders of magnitude, and I said, we can do nuclear physics, and we started new projects with respect to that. Between Livermore's investment, the department, some government investment, and the investments at the Stanford Linear Accelerator Center, there was about $220 million of R&D that went into the development of this technology before I came down here to Irvine. I generated 14 patents in the process of that, and we licensed those 14 patents, established the company, coincident with me coming down here to Irvine, right? The company is at 5201 California Avenue. Again, the intersection of Bison and California, or Drake and California, it's where the name changes. And we do all the manufacturing and R&D in that building. You'll see a lot of that as we go forward. In 2020, right as the pandemic hit, we took on a $12 million DARPA contract. They wanted to make a megavolt machine, not for medicine, but for industrial imaging. That is part of the support, but most of our support for the activities at 5201 is private funding. DARPA, it was nice having a DARPA contract. The pain of having a DARPA contract, we've got 5,000 pages of documentation that have been generated, right? I always like to say it's not a problem, it's a feature. It depends on how you look at it. I've got 5,000 pages of documentation now that would have been really hard to generate if I wasn't forced to generate it, right? There are many things you can do with this technology, and I could spend an hour basically talking about each one of these. I'm not going to do that, but you can break this chart down into 4 categories: precision medical diagnostics, novel medical therapies, industrial imaging and assay, and energy security and basic science. I'm going to talk about the things that have to do with medicine for the remainder, but many of these applications require that the source be compact and have high flux. Right? They also require that it be rapidly tunable from one energy to another energy with high precision, and that it be very narrow, very pure in the color when you go to one place. Okay? Now, I said something that was a little bit misleading at the very beginning here. I said that we make monoenergetic sources. I actually don't make a monoenergetic source. I make a unity bandwidth source, but my source has an angle correlated spectrum. I get 4 gamma squared, gamma being the normalized energy of the electron times the energy of the laser photon, as the on-axis photon. I get 2 gamma squared at 90 degrees. So if I do a head-on collision, I look on axis, I get 4 gamma squared, I get 2 gamma squared. Each angle has a different energy. That means that if I were to take the image that I'm showing here of the beam, oh, by the way, the beam looks elliptical. It looks elliptical because it's a dipole radiation pattern, right? And it's a linearly polarized beam, and the polarization, vertical, right? So that little donut pattern that you saw in your, I don't know, undergraduate E&M classes would look like that, okay? If I close an aperture, yes?
Is this a coherent beam or is it incoherent?
It's incoherent, okay? Coherence is the next generation.
Yes.
Yeah, okay? Actually, the incoherent nature of the beam makes the beam very, very beautiful. All right, and I'll get to that when I show you actual beam. This is numerical simulation. I'll show you actual beam profiles. If I close an aperture around this beam, I will narrow up the content of the spectrum that goes through that aperture. And if I keep closing it down, I'll get narrower and narrower until I get to a point where I don't make the bandwidth any narrower. I just take the amplitude down, throwing photons away. I call this the on-axis, minimum on-axis spectrum, and that's what we're trying to achieve. There are a number of things that contribute to the minimum on-axis spectrum. Obviously, if the laser photons have a wide energy spread, that's going to contribute. If the electrons have a wide energy spread, that's going to contribute. If you look at all of those factors, really, you end up with the conclusion that it's the electron beam. That you can make the laser beam have a contribution that's 10 to the minus 4, and the electron beam, if you optimize it, gets to 10 to the minus 3 out of the system. Typical Compton sources that people have produced to date are about 10% bandwidth. The 10 to the minus 3 is 2 orders of magnitude beyond where they're going, okay? We are interested, and we were interested at Livermore, and of course we're interested in a clinical scenario and having something that's compact. I want it to fit in a room that a CT or an MRI sits in, right? And I want it to be robust. I want it to be something where people can walk around. I can't have it be an interferometrically controlled system where walking on the floor is going to make it go out of whack. And I want it to have as narrow bandwidth as possible. From a compactness standpoint, if I'm going to build an accelerator, I want to build it with higher and higher frequency radio frequency, because the gradient that I can achieve before the copper structure starts to break down is higher, the higher the frequency of the RF I go to. We use X-band, which is 4 times the frequency of S-band. X-band, from a size perspective, is 64 times smaller volume than S-band. So it's also compact in that regard. We want to use shorter wavelength lasers because I need less electron energy to get the same X-ray energy the shorter the wavelength laser I have, right? If I want to increase the flux, I want to have a small amount of charge in each one of the bunches that's colliding with the electrons, colliding with the laser. The more charge I put in that electron bunch, the more electrostatic repulsion that bunch has, and the less likely I'm going to be able to focus it to a tight spot. So I want to go to a small bunch charge. I get a better electron beam out of that. I want to go to higher frequency because I get more bunches. And from a bandwidth perspective, I want to go to low charge because I get better electron beams out of low charge. And I want to do a LINAC versus a storage ring. I've asked me questions afterwards for the differences between the two, but there are 2 architectures that people have done in Compton sources. The storage ring will never get to narrow bandwidth as a route to go. All of these lead you to an idea that says, I don't want to put all the charge in one bunch. I want to take the charge and I want to put it in each RF cycle of the RF pulse that's going into my accelerator. My RF cycles in X-band are 87.5 picoseconds apart. My RF pulse is a microsecond in duration. I've got many RF cycles. People up to the time we started doing this were always putting as much charge into one bunch, not using the rest of those cycles, and then being limited by how good an electron beam they could have, right? So I'm going to show you the distributed charge Compton architecture that we have at over in 5201. In that building, in an office building, we have 600,000 pounds of lead and borated poly. During the pandemic, we actually came in and excavated the floor and poured 3 feet of concrete to build all of this on. The Irvine company didn't care. They said, as long as it looks like a concrete floor when you leave, we don't care, right? Which is interesting, right? The doors on this radiation enclosure are 25,000 pounds each. Right? We have 11.424 gigahertz laser systems. That's our particular frequency for X-band is 11.424. We have RF power systems that drive the accelerator, machine controls that operate, and then we have X-ray imaging systems that are on the back end. I'm going to show you the last 35 nanoseconds of operation. There's a train of 1,000 UV laser pulses that are heading toward the cathode of a photogun. That's a photogun. I'll pass that around in a little bit. Every time they hit the cathode, they liberate a burst of electrons. Those electrons are spaced by 87.5 picoseconds. They get accelerated to about 0.99 the speed of light in about 10 centimeters. And then they go into separate sets of accelerator sections that take them from 5 MeV to about 100 MeV. The electrons are then focused by the blue objects, which are magnets. The electron beam, by the way, at this point is about 2 times the diameter of a human hair. It's about 200 microns. It's going to get focused to around 5 microns. That's the ultimate goal of this setup. And then a separate train of laser pulses comes in and does a head-on collision with the train of electron bunches at a common focus. And every collision makes a little burst of X-rays, which is the white disk that comes out. The X-rays and the electrons are collinear until the electrons experience a large dipole magnetic field and get stripped out of the way. And then I have an X-ray beam that I can be using for imaging and diagnostics. So that's the cartoon version of how the distributed charge Compton source works. That's the real life hardware that's over in 5201 California. It's made X-rays now from 30 kilovolts to 100 kilovolts, 140 kilovolts. So we've spanned the complete medical diagnostic space. The accelerator itself has 3 sections in it and can go upwards of 100 MeV. 100 MeV, again, is enough energy that it can penetrate the body and be used to treat cancer. That's in the medical world considered to be VHEE, very high energy electrons. It is the most compact high energy electron system in the world currently. We make all of that stuff in 5201 California. Everything on this page is made there. Most of these things you cannot purchase anywhere commercially. I could go to CERN, I could go to SLAC, and I could get somebody to write a contract and get them to make me some X-band components, but I can't get any of these things commercially. I can get plenty of S-band and C-band, but I can't get X-band, the compact technology. Things like the photogun, I'm going to pass this around. This is scrap, so don't worry if you don't drop it on yourself, it's heavy, right? The RF power comes in the top square flange, goes into the gun. The electrons are generated at the flat surface at the back, and then they come out the conflat flange at the output. There are many steps in making a photogun, right? These are 15 steps that we use to make the photogun. It's specialized copper. We do all the precision machining. We do the diffusion bonding and brazing. We do the vacuum bakeouts. All of that stuff we do at that facility. That degree of vertical integration is unique, and it really is interesting. You know, when I was at Livermore, we had a photogun that looked very similar to that. And if I needed a new one, if I managed to break that gun, if I put too much RF power and it caused a discharge, it would take me a year to get a new gun. I would have to write a contract with SLAC. SLAC would then put us in the back of the machining queue, at the back of the diffusion bonding queue, the back of the diagnostics queue, at the back of the breakout queue, and a year later we would get a photogun. In principle, if we really had to, you could go from zero, from raw metal to an assembled gun in 5 days. That fundamentally changes the whole R&D cycle. We are, I think, have installed gun 13 in the system right now, right? You know, we're not 13 years into doing what we're doing. From the laser perspective, I think this is an interesting topic. We don't use mode lock lasers in our system. Mode lock lasers typically run at 100 megahertz. We want to run 100 times higher repetition rate at 11.424 gigahertz. So what we do is pulse synthesis. We start with a CW laser, very narrow line CW laser. We pass that CW laser through telecom quality phase and amplitude modulation. Amplitude modulation first to make a train of 50 picosecond pulses at 11.424, and then into phase modulators that allow us to add bandwidth, create a chirped pulse, and then we can amplify that chirped pulse in fiber amplifiers and do pulse compression on it and have a train of 11.424 gigahertz pulses. That train of pulses is at exactly the frequency of the accelerator because I use the RF of the accelerator to drive the modulators. So all of the synchronization problem that everybody who's done laser Compton before has kind of dropped away. I've got it all naturally synchronized between the two. We've done a number of demonstrations for this system. I'm going to walk you through some of these. For those demonstrations, we have the source, place where it's generated. That's where the X-rays come out. That's the collision point for the laser photons and the electron beam. The laser beam is roughly 5 microns at that spot. There's a window, either sapphire or chemical vapor deposition diamond, that allows the electron beam or the X-ray beam to come out. We have a table that we can manipulate an object, radiation tubes. These are lead-lined tubes that allow us to put the detector outside of the radiation enclosure, and then the high-resolution detector system. By the way, I have to make my own detector systems because clinically nobody has a 10-micron resolution detector system. They have sources that are 600 microns, so they don't have any motivation for making high-resolution detectors, right? Talk a little bit about the output. That is data. That's not a numerical simulation of what the X-ray beam is. Each electron is emitting its own dipole radiation pattern, and the reason why this looks so beautiful and smooth is that it's emitting it from a 5 micron area, and the beam, by the time it gets there, is 5 to 6 centimeters. So each one of those emitters has uniformly overlapped with each other. So the incoherence of this gets rid and makes a beautiful smooth beam profile out of the system. Now, I said it was angle correlated, so the on-axis in this case is close to 55 kilovolts, right? The on-axis 55 kilovolts. If I go to a wider angle, 5 milliradians in here, I'm at the place where I have 47.4 kilovolts. Well, you know, if I look in the periodic table, every element in the periodic table has a unique X-ray energy where there's a discontinuous jump in the X-ray absorption. That point is called the K-edge, And that is the point at which the X-ray energy is sufficient to remove the 1s electron from the atom. Below the K edge, you get more transmission. Above the K edge, you get more absorption, right? So I get preferentially transmitted if I have below the K edge and preferentially absorbed if I'm above. I can do a very simple experiment. I can take a foil of material, put it across the entire beam. Those photons that are above the K edge are going to be preferentially absorbed, and those that are below are going to be preferentially transmitted, and I will get a hole in my beam. And the edge of that hole is exactly the K edge of the material. So I have a spectrometer built into my setup simply by putting a foil in. I know exactly at what angle I get 50.2 kilovolts, and that's the gadolinium K edge, and I can work from there to what the on-axis energy is and what the energy is anywhere else in the beam. Right? You can use that for tuning. So we did different sets of foils, terbium, gadolinium, neodymium, 50.9 kilovolts, 44.9, 59 kilovolts. You can see the hole changes as you go across this whole series, right? We actually had a DARPA milestone that said you had to tune from one energy to the other energy, and you had to get there with 1% accuracy, and you needed to do it in less than an hour. And the first time we tried it, we did it in 9 minutes, and we didn't have any computer control, right? So this technique works really, really well in doing that. One of the other things people care about is the bandwidth. The hole that I make, the crispness of the edge of the hole, is determined by how much energy spread I have on that on-axis portion of the beam. I have a measurement, and then I can fit the measurement to a beam profile by changing what the on-axis bandwidth is of the system, and 0.4% RMS is about the right answer. 5% is the best result you'll find in the literature beyond what we've done, right? And clearly it's not a 5% fit for that arrangement, okay? I'm going to talk a little bit about medical applications. So these are the 4 cases for medical applications. I'm going to start with using the K edge, right? So, sorry. I do element-specific imaging. So again, I can have different K edges allow me to look at different elements. There are many cases where people will inject into the body a different element to use it as a contrast agent for finding a disease. Gadolinium is a common contrast agent that is used for doing magnetic resonance imaging, and iodine is a common contrast agent that's used for X-ray imaging. In both cases, if you're looking for cancer, it's the extravasation around the cancer, the leaky vascular structure around the cancer, is where the accumulation of that contrast agent will be. All cancer grows its own vascular structure. It wants to be fed. That's how it takes over you, is that it tries to grow and grow and grow. It has to be fed. But that vascular structure isn't as good as the vascular structure in your body. And so if you feed this contrast agent in, it will accumulate in those areas, and you can use that to look. So below the gadolinium K edge, less absorption. Above, we have something else, right? We have more absorption. We made an object to look at. That object had copper, tungsten, gadolinium, and borated poly. By the way, there are 2 million gadolinium-based MRIs done in the US a year, right? They take an hour to do this process. Inject, person lays on the table, go into the tube. An hour later, they get a millimeter resolution of the gadolinium, right? What we can do is we can, instead of making 2 color of beams, what we can do is scan the object through the beam and record the data as we're moving the object through the beam, and one portion of the beam will be below the K edge and another portion will be above the K edge. So in this mode of operation, I would move the object through the beam to keep track of where the object was relative to the beam as I did it, and I would get the subtraction image. So this is the image with photons that were below the K edge. That's the image of the photons above the K edge, and now I can subtract them. Well, when I subtract them, all of the other elements have roughly the same response for those 2 energies, above and below, except for gadolinium, and I get a picture of the gadolinium, right? So that makes the things jump out in really strong fashion. This is done clinically. Both GE and Siemens have devices that do breast cancer imaging using iodine as a contrast agent. We did a numerical study of this in my academic group. One of the PhDs, MD PhD students I had did this study, where we took a FDA-approved package that allows you to simulate any tissue in the body. So we simulated breast tissue. We took the 4 cases that are hard from a breast cancer perspective, dense, heterogeneously dense, scattered fibroglandular and fatty tissue. It's a numerical model. We can add cancerous lesions. That's what the yellow dots are. And it's a numerical model. We can add iodine to the cancerous lesions in various amounts. If I were to take the GE device, which uses a brim tube above the K edge and a brim tube below the K edge with a big broad spectrum above and below the K edge, so the subtraction isn't very good. If I use the brim tube and 0.1% by mass, that's what you see. You might, if you squint hard, be able to make out the one lesion I'm trying to point to with the arrow. This is what you see if you've got monoenergetic X-rays. It's between 30 and 50 enhancement in contrast, which means you could do 30 to 50 lower dose. I mean, there's all sorts of advantages for doing that. That publication came out in MedPhysics back in December. It is also the basis of an FDA submission that was made in December. In the FDA submission process, you can ask that your device be declared to be a breakthrough technology device. Breakthrough technology is higher efficacy or lower damage to the patient. We submitted that paperwork in December. On my birthday in January, they sent me the notice saying we're approved for the breakthrough device designation. So good birthday present. That's not an approval. It's a fast track on the approval process. Okay, we're about 12 months away, and in fact, really, we're limited only by our ability to generate the thousands of pages of paperwork that are required for that approval. The next thing I want to talk about is high-resolution imaging. Pass this around. Okay. I'm going to image a flat piece of tungsten that I've laser cut that tungsten to have an Air Force resolution pattern in it. You're looking at 6 millimeters of the 25 millimeter object that's going around the room, and the smallest features in that object are about 30 microns, about 1/3 the diameter of a human hair. If I were to image this object with a standard clinical X-ray tube, a 600 micron spot X-ray tube, this is what you would see, right? You won't see any of those features because the spot size is way bigger than the features you're trying to image. This is what we see, right, with the detector that we built at Lumitron. So if I'm trying to find disease, do I want to look at it at that resolution or I want to look at it at this resolution? It's roughly 100. 100 is nominally the same, nominally the difference between the size of your thumb and pulling out one hair and looking at the size of a hair, right? So we've also done something called phase contrast imaging with this machine. Phase contrast imaging does not exist in the clinic. When you go to the clinic, you have the option of getting an MRI or getting an X-ray image. The X-ray images give you relatively good resolution, but they can't see soft tissues. They see things by the absorption difference of the dense materials versus less dense materials. You have the MRI to see the soft tissues. If you have a small X-ray spot, you can actually do something that allows you to see soft tissues with X-rays. So in normal absorption imaging, the bone is more dense than the flesh. You see the shadow. If I'm taking a picture of a mouse, we didn't take this picture, by the way, this is out of the literature. If you take a picture of the mouse, you see the bones of the mouse very well, but you don't see the lungs, the esophagus, any of the soft tissues in the mouse. If I can make the X-ray spot small, I can have X-rays that go through the object and bend, and X-rays that pass around the object and bend, and they can cause an interference at the detector that is indicative of the location of the interface between those two materials. And that interference can be used to give you the location of the soft tissues. So that same mouse in phase contrast, you can see the lungs and the esophagus and everything else that's there. If this X-ray spot gets big, of course, I now have many paths that blur out that interference, and I can't see the interference pattern anymore, right? We did a simple experiment. I actually sent people out to H-Mart, and they came back with a green bean, a dried anchovy, and a chili pepper, right? If you do an X-ray absorption image of that, well, it's the same image. It's just what you're accounting for. You can see the spine of the anchovy. 300 microns in diameter, the spine of the anchovy. But the really interesting thing are the seeds and the chili pepper. Because I'm seeing seeds underneath seeds underneath seeds. And if I were looking just in absorption, I would never see that. The top seed would block out everything that's below. So I'm actually seeing phase contrast enhancement in this image. Phase contrast imaging is something that has been done at synchrotrons. It has been studied for clinical applications at synchrotrons. There have been many wonderful outcomes from those studies, all of which suggest that phase contrast would be revolutionary to medicine, all of which end in a publication that says this is great, but it's clinically impractical to take people to synchrotrons, and this won't be useful until there's a compact monoenergetic X-ray source. Hey, I like to have free advertising, right? This is the third largest synchrotron in the world, the European Synchrotron Radiation Facility in Grenoble. I've actually done experiments at this facility, not the experiment I'm going to show you. That's a, excuse me, go back. It's a $600 million facility. They did a $150 million upgrade in 2021 to take their electron beam from 200 microns down to 10 microns, right? And with that, they did whole organ phase contrast imaging. These are cadaver organs. It's not a live human. The dose that they're giving would kill a human, right? So don't get excited that we're going to do this. They take 20,000 separate projections to get you the image that you're going to see. But this is what kind of thing you can do. So this is a human heart. Notice the scale bar is 30 millimeters. It's a 3D data set with 20,000 images in it. And now they're going to zoom in on that 3D data set. I'm going to go in about a factor of 200. Long way from being done. Still not done. At kind of this level, you're histological. If you did a biopsy and you pulled the material out and used a keratome and you put it under a microscope, this is the kind of thing you might see, right? The potential exists for doing virtual histology. You don't need 20,000 images to take a picture like this. So that's really useful. Now, I didn't make this image. It was made at ESRF. Why did I want to show you this image? There were three attributes that were used to make that image. One, it had to be 80 kilovolt X-rays. That's high energy for a synchrotron, not high energy for us. We've done 140. It came from an 8 micron spot. We have a 5 micron spot, so that's not hard. And they needed 1.4 times 10 to the 11 photons per second to be able to make that image in a day, right? The setup that we have at Lumitron is on track to do greater than 10 to the 11 by the end of this year, right? So sometime at the end of this year, we hope to be doing HIP-CT images with this kind of technology. The last thing I want to talk about is the electron beam radiotherapy and image-guided radiotherapy. There's a nice review paper that we published in Frontiers in Physics back in December. As of this morning, it's had more views than 55% of all papers ever published in Frontiers in Physics. So it's doing well, that paper. I'm going to talk about a number of the different areas. I'm going to talk first about VHEE and how VHEE works, right? Let's use lung cancer as the case that we want to look at. So I've got a nodule in the lung cancer that I want to try and treat with radiation. I could use high energy X-rays to treat that radiation. I could try and get to this region inside the body. This is the entrance on the left, and the lung cancer is sitting here. And if I use high energy X-rays, I can get there. But if you look at this curve, I'm putting most of my dose at the surface. I go exponentially in. Now, I can reduce the dose to the surface relative to the cancer by doing stereotactic illumination. I could illuminate you from this direction, illuminate you from this direction, illuminate you from this direction, make the beams overlap where the cancer is, and I've reduced the dose to the surface tissue and increased the dose to the cancer. Right? Protons are the gold standard. Protons, if you have a proton beam with the right energy, the Bragg peak will cause that proton beam to stop within a millimeter of the place you want to go. So if I choose the energy correctly, I can hit that lung cancer really nicely. Protons work really great for things like brain cancer, where the material that you're going through is homogeneous. They don't work so great for lung cancer because you're going through bone, flesh, empty cavity before you get to the lung cancer. And if you get the energy wrong, you deposit all that energy in healthy tissue, and you kill the healthy tissue really, really well. So what do the protons do for lung cancer? They turn the energy way up, and they operate in pass-through mode, where they give roughly the same dose going all the way through, and they stereotactically illuminate again. Well, that brings us to VHEE electrons, because VHEE electrons, high-energy electrons, have a dose profile that looks like this. So you could do a stereotactic illumination, where I go from 1 fraction, 2 fractions overlapping at the same nodule, 3 fractions, 4 fractions, 5 fractions, and now I have a dose profile that looks kind of similar to what a proton beam profile looks like, but it's not a proton beam. Proton beams, by the way, proton beam clinic is about $150 million. It's about the size of 5201 California Avenue. And if you did that with VHEE, it would be a much smaller, much cheaper device. It is the reason why the oncology world wants to have VHEE electron beams, right? Because they don't, the problem with the proton machine, if it's $150 million and you treat 500 to 1,000 patients a year, the treatment cost is $250,000 of treatment. You know, you've got to be pretty wealthy or have one hell of an insurance policy to be able to have proton therapy, right? If you can get that down into the few $1,000,000 range, then you know you've got some equitable way that you can start treating cancers and maybe do it a little bit more rapidly than what protons do. By the way, a 250 MeV proton beam, this is the dose deposition profile in a bucket of water. You're basically water, right, when it comes to particles and stopping of particles. So if I take the proton beam and I go in the entrance on the left and I go through and I look at what the attenuation is that's going on and what the energy spread is or the spread of the beam is going on, that's the profile I get, the heat map that I get. 350 MeV electron beam looks exactly the same, right? So that's, again, the reason why everybody's interested in 350 MeV electrons. It doesn't require the same kind of space, which kind of brings me back to the compact distributed charge nature of things, right? I had a VHEE machine at Livermore. It was 30 meters long. It was based on S-band LINAC technology that was developed at SLAC for the original SLAC accelerator. There is a VHEE capability that's used for studies at CERN. It's called CLEAR, and it's about 40 meters long. And that's kind of the footprint that you might have if you go to X-band. Right. So again, the reason why everybody wants to go there. The last topic in that title is flash radiotherapy. When you do a standard radiation treatment, let's say you do have lung cancer, they're going to put you on the table. They're going to bring the radiation source in. They're going to give you 10 gray over about 30 minutes. 10 gray, by the way, a gray is a joule per kilogram. So you're going to give you 10 joules of energy per kilogram of U. They're going to do it over 30 minutes. And then they will send you home. And they'll bring you back in a week or so, and they'll give you 10 gray again. They'll send you home, and they'll bring you back. They'll do it 3 or 4 times. They can't give you 30 or 40 gray at one time because it would kill you. And the game that they're playing is, can we kill the cancer faster than we killed the patient, right? It's the same game you play in pharma, right? Flash is, don't give the 10 gray in 30 minutes. Give the 10 gray in a microsecond. And what happens is that you end up sparing the healthy tissue. You still kill the cancer, but you spare the healthy tissue. There's a lot of debate about why. We have people on campus that have their theories. My group has theories. There are people all over the world that have theories. There's not been a debate about whether the flash effect is there since the 1970s, right? But why, that's still a big debate. This is a study done by Marie-Catherine Vosnin's group in Switzerland. She's one of the world leaders in this capability. This is actually a picture of living pigskin. So it's a live animal that has been irradiated with 30 gray over tens of minutes. And you can see the charring on the skin, right, from that irradiation. It's damaging. That's the same pig, 30 gray in a microsecond, right? So you're sparing the healthy tissue when you do that. Marie-Catherine's group has actually done a patient, a human. They looked at a cutaneous lymphoma, skin disease. You can see 3 weeks, 5 months, disease is gone, right? Problem with this was it was done with 5.6 MeV electrons. That's the energy of the electron that comes from a standard clinac. The thing that makes the X-rays can also be used to make electrons. 5.6 MeV electrons go about 1 centimeter into the body. So you're not going to treat cancer everywhere in the body doing that. It's good for the surface, but it's not going to be good for the whole body. We did a little setup at Limitron to see this arrangement, and what we did was we replaced the output window, which was sapphire, with 100 microns of CVD diamond, right? We need to have a window that we can transmit the electrons through. That's 99.9% transmission for the electrons, 100% transmission for the X-rays, right? And it's strong enough that it holds off vacuum, because I have 10 to the minus 9 torr vacuum on one side and atmosphere on the other side, right? And I don't want to have atmosphere get into my 10 to the minus 9 torr vacuum. So we have a window, we have a scintillator in the way. So when the electrons hit this scintillator, they make visible photons. There's a mirror that deflects those scintillated photons onto a camera, and we can measure the beam profile of the electron beam, right? And this is the electron beam that came out. with 1,000 microbunches at 50 MeV, that's 10 nanocoulombs in 1 macrobunch. 10 nanocoulombs in 1 macrobunch is equivalent to 10 gray in 100 nanoseconds. Right? So this is a flash beam. There have been a number of flash studies done around the world over the years. The X's on this plot are flash studies that did not show the flash effect. In other words, they used conventional radiation, they used what they thought was flash, they compared the results at the end, and they didn't see a difference. The circles are where they did see the flash effect, right? So no flash effect, flash effect. The item down at the bottom right-hand corner, you want to go fast and with a lot of gray per second, was a giant electron beam accelerator in the 1970s. It was what started everybody being interested in flash, right? Too big to be practical, but very interesting from an experiment perspective. All of the other results that are close to it are all low energy electrons that can't be used for generic cancer treatment. They can be used in small animals. Easily use them in small animals. Mouse cancer, it'd be easy to use those, but you can't use it in a human. This is where the capability at 5201 was in December of 23. Right? It is, as far as I can tell, the first and only compact VHE flash capability in the world, which is great. We are on our path to do our first animal studies this summer. We're partnering up with Charles Lamoli's group here on campus. We're going to do 4 cohorts of mice. 1 cohort stays in their cage and are happy. The second cohort gets 10 gray to the whole brain over 10 minutes. The third cohort gets 100 gray per second, 10 gray exposure. And the fourth cohort gets 10 to the 8 gray per second, 10 gray exposure. So the beginning of that, beginning somewhere up here and somewhere down here, right? And the idea after that is that you take the mice, you let them live for a couple of months, and then you run a maze test. And you look to see if the mice that were unirradiated and the flash irradiated have similar cognition compared to the ones that are conventionally irradiated. Right? There's a lot of belief that that's going to be the case. I mean, after all, if I'm going to treat your brain cancer and I manage to cure your cancer, but I erase all your memories, is it a good thing? Kind of depends on your life, I suppose, but right, it is a question. So we're going to do those studies sometime later in the summer. Another set of studies we're doing is with Professor Christopher Hughes' group here on campus. Chris Hughes is famous for having an ability to grow cells in a vascular matrix that can be microfluidic fed, and so you can have blood going. It can be an in vivo-like setup for the cells. This is great because now I can put iodine, gadolinium, gold into it. I can, do different cancer studies using the gold or using photoactivation of those elements to try and kill the cancer or to image the cancer. I can do electron beam studies. They're much more rapid to do and much less cumbersome to do than the mice studies. That will start in July. We've had our first kickoff meetings and we're going to be moving forward. I'm going to end with the image-guided nature of this setup. The electron beam came out of this arrangement. I described how Compton scattering worked. I said we have an electron beam, it's moving at the speed of light, near the speed of light. We have a laser beam that collides with it. Which direction did the X-rays go? They went in the direction of the electrons. They didn't go in the direction of the electrons because I engineered them to do that. They went in the direction of the electrons because nature sends them in the direction of the electrons. When I'm doing X-ray imaging, I bend the electrons out of the way. I use a magnet, get them out of the way. And then I have my X-ray imaging beam, right? I could use that beam, and it's in the same absolute direction as the X-ray beam, which leads you to a possibility for image-guided radiotherapy. Okay, I'm going to end with a little animation that's going to describe breast cancer detection and treatment, right? In the US, 40% of women have dense or thick breast tissue. Dense and thick does not mean large. It means that you can't see the things you want to look at. Right? And in fact, standard mammograms now, if you are a dense breast individual, the radiologist has to let you know that you are a dense breast individual because 70% of the time you get a false positive or a false negative. Okay? False positive, you've got a lot of trauma. You think you've got cancer. False negative might kill you because you walk away thinking you don't have cancer and you do. right? So for those women with dense or thick breast tissue, they will sometimes forego a standard mammogram, pay out of pocket nearly $1,000, and have a gadolinium-based MRI. Injection with gadolinium, gadolinium accumulates in the leaky vascular structure around the cancer, lie on the table, go into the tube for 30 to 45 minutes, come out with a millimeter resolution image of the breast. One advantage of that, there's no compression of the breast in that mode. They lie on a table and the breast hangs freely below. So that's a good feature. 45 minutes, millimeter. You could do that in minutes, and you could do it with micron resolution. So the throughput for the hospital would be much greater, and the benefit to the patient would be much greater. And by the way, the dose that you would give to the patient is a fraction of the dose you would give in a standard mammogram. At the same time, you're making an electron beam that goes in exactly the direction of the center of the X-ray beam. So let's run a little animation here. We're going to be in the Center for Radiological Health Sciences or Services. We're going to go into the treatment room, or the detection and treatment room. Machine is inside of its little radiation enclosure. The technician in the room is going to align the patient to the path of the beam. The patient is lying on a table that has a cutout for the breast to hang freely below again, so that there's no breast compression in this arrangement. The path of the X-ray beam is outlined by a set of low-power laser beams. Think of the red laser in a grocery store scanner, right? The clinician in the treatment room or the detection room can then align the patient to one side of the beam, scan the patient through the beam to get a 2D image. We look at that image, and if you decide that, well, that doesn't look like it's good, we should try and treat that. What you'll do is you'll move the patient close to the source where we can use the electron beam, and you'll take one more picture. You take another picture to make sure you know exactly where the cancer is, and then you will align the patient so that that cancer is exactly at the center of where the X-ray path was. So we do one more picture, find the cancer again, move the patient so that that cancer is centered on the X-ray path, turn off the X-rays, turn on the electron beam, and you're done. Now, in principle, like, you get up and go home, right? That would be the vision of what we want to see happen. We're a long way from there, but that is kind of the driving force behind, what we're trying to do right now. I'll end there. I'll say that, what I've talked about has involved a lot of people. There are about 50 people over in the company right now, not all of whom are in this picture here. I have an academic group. Not all the people who have been in my academic group are in that picture. The picture in the middle is the interns that are here this summer. We've had, in the last 4 years now, 60 undergraduate interns come through the company working in various different activities. It's always fun to have them around. It's extra, inquisitiveness with respect to the things that are going on. Hopefully they're watching this in fact, they are. Wave, interns. You can wave. They're upper left-hand corner. There you go. Okay. And with that, I'll stop and open for questions.